We have discussed the mechanism of all type of walls, but we will look at the design of only this cantilever retaining wall. Okay. So this stem has tendency to deflect like this. Okay. So the earth behind this will have tendency to move in this direction. So these are create active type of earth pressure, and if there are soil in this side also, then there is tendency that this due to rotation of this stem, that stem will compress the earth here, and one reaction will be exerted by the earth to the wall, and that is passive pressure. So that is induced due to compression of the soil by the retaining wall, and these are active pressure. Okay, so the type of earth pressure is active earth pressure or earth pressure PA, and the passive earth pressure PP. So active earth pressure tends to deflect the wall away from the backfill, and passive earth pressure will be like a restoring force. It will oppose the movement. Now, suppose this KE is the coefficient of active earth pressure. Okay, so the distribution of this pressure, active earth pressure, will be like this triangular. That will be maximum at the base of stem. Okay, and it will vary linearly. So at a distance h, if we want to calculate the maximum pressure at any height, that will be Ka gamma. Gamma is the unit weight of soil, and h is the height of this point. Okay, so this will be the pressure at any height. Now we know the pressure. So to calculate the total pressure at any height, this will be the pressure Ka gamma h. So this is Ka gamma h. Okay, into half. This is gamma h. This is h. So into h, and this is triangular distribution. So the total pressure will be half into, and the unit width of 1 meter. This is for unit width of 1 meter. So the pressure will be half of Ka gamma h into h. It will become Ka gamma h square over 2. Okay, so this pressure is for 1 meter straight. So bending moment at any height. So now this is the pressure. It will act h by 3 from here. So if we want to know the bending moment at this location, this will be this pressure Pa into h by 3 lever arm. So it will become Ka gamma hq by 6 over 6. So the total pressure at this point, which is maximum height, okay, will become, with the similar equation, Pa equal to Ka gamma h square over 2. This is the total pressure, and the total bending moment will be this at height h equal to. Okay. Now, where this Ka is the coefficient of active earth pressure. So this coefficient will be equal to Ka will be equal to 1 minus sin phi divided by 1 plus sin phi. This is Rankine theory, where phi is the angle of friction, angle of internal friction, or angle of repose. Here it is given. Okay. So if, and Kp will be inverse of Ka, so it will become 1 plus sin phi divided by 1 minus sin phi. Kp is the coefficient of passive earth pressure. So this will be passive pressure here. So this is coefficient of passive earth pressure Kp, and this is coefficient of active pressure Ka. So Ka will be equal to 1 minus sin phi over 1 plus sin phi. Kp will be equal to 1 plus sin phi minus 1 divided by 1 minus sin phi. So actually K inverse of 1 by Kp. Okay. So that is 1 over Kp, coefficient of passive earth pressure. Gamma is the unit weight or density of the backfill. If we assume phi equal to 30 degree, which generally occur in case of sand, so in that case K will become 1 over 3. 1 minus sin 30, 1 plus sin 30. So 1 minus half, 1 plus half. So it will become K equal to 1 over 3 and Kp become 3. So you see from here that the coefficient of passive earth pressure is 9 times coefficient of active earth pressure. So the coefficient of passive earth pressure is much more than the coefficient of active earth pressure. Okay? But
hello sir, sorry for interruption. That K formula 1 minus sin phi divided by 1 plus sin phi, it will not be equal to tan square phi, I think.
1 minus?
That formula 1 minus sin phi divided by 1 plus sin phi.
Yes.
Whether it, I'm not getting, equal to tan square phi. Whether it is correct, tan square phi.
Okay. ये करेक्ट है, कहीं से तो मैंने लिया है इसको, बट ये ट्रिग्नोमेट्री से भी पता चल जाएगा अभी. So the coefficient of active earth pressure for horizontal fill will be equal to 1 minus sin phi plus 1 plus sin phi, and for inclined backfill it will be like this. We will have to include this theta. If you assume that theta equal to 0, this equation will become this equation. Okay. Here theta is the angle of inclination and phi is the angle of internal friction or angle of repulsion. Okay. So this active earth pressure will act like this. This has two components, one horizontal, other vertical. Okay. So these are active earth pressure. Passive earth pressure will be like this. Okay. Since this is horizontal, so the direction and the force will not be inclined. It will be horizontal, and the backfill will apply this W force on this heel slab, weight of soil above heel slab. This will be the soil pressure, will be like this. So the resultant soil pressure is R, and there will be friction between this soil and this bottom of base, that is bottom of heel slab and toe slab. Okay, and this pressure will act at a distance h by 3 from here. Okay, so from here we can see this will be pressure like this. So in this portion there will be net, since this pressure is more. Okay, so in this portion for this toe slab, net pressure distribution will be like this. Okay, so this is the critical section. We will have to calculate shear force and bending moment at this section, and we will have to calculate the magnitude of this force. The distribution is this distribution. This soil pressure will be less the pressure exerted by the soil which is resting above the hill. So here the net pressure distribution will be like this, and we will have to calculate the maximum bending moment and shear force at this location. So this is C. So this is C and this is D. So we will have to calculate the value of C and D. But here the bending moment will be like, the deflection will be like this, and here the deflection will be like, both will act like a cantilever slab. Okay, and for retaining wall, this stem also we will have to calculate the distribution. So for stem the force distribution or the pressure distribution will be like this. We will have to calculate the critical value at this location, at the junction of this base slab and stem slab. मेरी आवाज क्लियर है ना?
Clear hai sir.
Yes sir. Okay. Now you see the behavior of retaining wall. As we have already discussed, this stem will deflect like this. Okay, due to this pressure, the net pressure on the heel slab will be like this. Okay, so it will deflect like this, and the net pressure on the toe will be like this pressure, and it will deflect like this. Okay, so this is to design the retaining wall. So we have checked till now the strength of the retaining wall. Now we will also have to check the stability of the retaining wall. So there are two possibilities that the first is the retaining wall will have tendency to overturn about this point A. Okay. So the disturbing force will be this active earth pressure, and the restoring force will be this force, the force on the base due to this soil, due to disturbing force. So we will have to calculate the moment at this point A due to this active earth pressure and the due to the soil load over the hill slab and the overall weight of the retaining wall. Okay? Now, this retaining wall will also have tendency to slide, okay, due to this active earth pressure. The restoring force will be this passive pressure, and the friction which is being generated at the interface of soil and the bottom of base slab. ठीक है, यहाँ पे एक प्रेशर होगा, frictional pressure, that will resist this disturbing force. So we will have to check this retaining wall for sliding of wall, for overturning of wall, and we will also check the heel, base, and stem slab for strength and serviceability. Okay. Now we will discuss one problem, that is analysis of retaining wall of 7.2 meter fill height. Okay, so these are the dimension of retaining wall. This is the angle of inclination. Suppose this is theta. So the height, this is given height of earth filling. So this is the height of earth filling from the ground level. Here is this one. And the ground level at this point is this one. So this is the height of fill, 7200 mm. This is unit weight of soil. Now we will also calculate the surcharge weight over here. This is surcharge. So as per clause 2141 of IRC 6, the surcharge is taken as 1.2 meter fill height. Okay. Angle of internal friction is suppose 35 meter. Angle of inclination of fill is 0. That means the fill is horizontal. और screen दिख रहा है?
Yes, sir.
Okay.
Yes.
Unit weight of soil is suppose 18 kilonewton per meter square. That is surcharge. So that is actually as per IRC clause 214.1 of IRC 6, live load surcharge is taken as 1.2 meter of fill height. So if you multiply 1.2 meter into 18, you will get this. Okay. So angle of internal friction is 35. Angle of inclination of filling is 0. That means the fill is horizontal. Angle of friction between the wall and the earth fill. So this between this wall and earth fill. So this is angle of friction here will be each suppose 12 degree. Okay. So the coefficient of friction between base concrete and the soil mu is 0.65. Grade of concrete is 25 MPa. Steel is 500 MPa. SBC of soil is taken 1500. You take this 2000. Suppose 2010 per meter square. Okay. So height of stem will be, it will depend on the, so the height of stem will be equal to 7950. So this is from 7200 plus 750. Okay, from here. Because we are interested at this location. The bending moment and shear force of this location. Okay, thickness of stem at top, suppose this is 500. Taken 500. Thickness of stem at base 1000, width of fill 2400, thickness of fill 750, width of 2 is this, thickness of 2 800. So here one error, you generally keep the thickness of 2 and the thickness of fill equal. Okay, so you assume this also at 800. Depth of foundation we have taken 1500 and total weight of foundation total width of foundation will be equal to 5,000 mm. Okay, so that will be equal to this 1600 plus 1000 is the depth of stem here plus 2400 the width of heel. So this 2400 width of heel is taken slightly more than this width of 2. Okay. Now, if phi is 35, alpha is 0 and delta is 12 degree, we can calculate this Ka by this equation. This is 0.27. Again, we have also calculated this K, the friction between the wall and the earth fill. Here we have considered the friction between the wall and the earth fill. That friction will reduce the coefficient of active earth pressure. So if we consider the friction, it will come 0.25 for the same case. Okay, without friction, it is 0.27. Okay. Now we have seen how to calculate this PA. So now this PA, we have also seen that the force will be half Ka gamma h square. H is the height. Okay, this is the PA pressure due to surcharge. Okay, so due to surcharge, what will happen? This is Ws. So if this is the retaining wall, due to surcharge, there will be uniform pressure, and due to active earth pressure, the pressure distribution will be triangular. Okay, so this is for this distribution and this is for surcharge 2. Okay, so the total PA is equal to this. So from this we have calculated this PA. So from this we can calculate the tentative dimension of our retaining wall. Okay, so the width of base will be equal to 2p over 3p over 2 gamma for tentative width. So total width you can take around is 4.26 meter. We have taken 5,000. Toe width will be equal to 33% of this. We will take or keep the width of heel slightly more than toe width. Width of stem at base, this is approximately equal to h by 12. H is the heel height. So in our case, this will be 0.725, so 0.7 meter. Hence width of heel, that will be this minus this minus this. Okay, the total base height. So these are tentative dimension. Okay, so accordingly we will fix our dimension. And thickness of heel will be equal to approximately h by 10. So this will come this 0.9. So keeping this in view, I have fixed my dimension. Now we will calculate the active earth pressure at the base. The horizontal earth pressure at the base will be equal to, so due to friction, the pressure at the wall will be slightly inclined. And we will have to take horizontal, this and this is delta. So the earth pressure at base will be 39.29 kilonewton per meter square, and the horizontal earth pressure at base will be equal to PA cos delta. And the horizontal pressure due to surcharge will be like this. We have already calculated this into, we have calculated the pressure Ka Ws into H, and Ws we have calculated the surcharge at this 21.6. Okay, so 21.6 into height into Ka. Now we will calculate these values. Okay, these values. Now you see stability calculation. So active earth pressure will be, so this will be active earth pressure, pressure due to this active pressure plus pressure due to surcharge. The pressure due to surcharge will be uniform. It will act at this position at the center. The pressure due to this is the earth pressure. Pressure will be triangular. 0 here and some value here. So now I have calculated this active earth pressure 5.42. This is the pressure. This is the height 8.70. See, this is total height from here to here. We are calculating the pressure below this base. We'll take height from here to here. So this is the pressure into height, total horizontal force, the distance from point A, and we will calculate the distance from point A, from this point. Okay. So the distance from this point will be 4.35. This is half of height. This from here to here. Because this was the force, and the bending moment will be this force into this lever arm, Z. And the lever arm for this force will be like this. This is Z. So these are for surcharge, and this is for active earth pressure. Okay, this is total pressure, and here this lever arm will be H over 2. This lever arm will be H over 3. So we will calculate the moment about A. This is the total horizontal force, and this is the moment at A due to this horizontal. That will be due to active earth pressure. Pressure due to surcharge plus pressure due to earth filling. Okay, and the restoring force will be the wall, the base, backfill, and the surcharge. Okay, the restoring force will act for this surcharge, for this backfill. Sorry, this will act here. We will calculate the weight of this filling. Then, due to this surcharge, that will also act here at this center. So the lever arm will be this. Okay, for this base slab, the lever arm will be this at center. For this stem, we will divide this into two parts. This is one part. We will calculate the weight. The lever arm will be this from here to here. And for this triangular part, the lever arm will be this distance. Am I audible?
Yes, sir.
समझ में आ रहा है ना कि कैसे लीवर आर्म कैसे स्टेबिलिटी में चेक कर रहा हूँ. Okay, so the wall we have for this stem wall we have divided this stem into two parts, this rectangular and triangular part. So this is the rectangular part. 25 is the unit weight of RCC. This is the triangular part. So these are vertical load. This is the lever arm from point A. So moment at about A will be this. This is for base slab, total slab. This is for backfill, which is above the hill, and these are the surcharge above the hill. The total moment about A will become this 2066.03 kilonewton meter, and the total force will become 638.09. So this is the vertical force, and this is the moment about A. This is the horizontal force, active earth pressure, and the moment about A. So this is disturbing moment, and this is restoring moment. This is disturbing moment. These are restoring. So the restoring moment is more than, I think, approximately three times of disturbing moment. Okay, so the factor of effective safety should be more than 1.5. So now we have calculated the moment about A, the active earth pressure, and the vertical restoring weight, the weight of this heel slab, weight of the retaining wall plus weight of due to surcharge and due to backfill above heel slab. Okay. Now we will calculate the axial load, vertical axial load, and the bending moment about the centroid, so that we can calculate the base pressure. Okay. So what we will calculate? We will calculate we have calculated. So this is the retaining wall. So we have calculated this pressure PA. This is the point A. We have calculated the bending moment about point A. Okay, due to this active pressure and due to weight of this filling, surcharge, and the weight of the retaining wall. Okay, now we will calculate suppose this is 5 meter. So now we will calculate the moment centroid of this section, 2.5 meter from here. Okay, so total moment about A is this one, the restoring moment, and this is disturbing moment. So net moment is this one. Total vertical force we have calculated due to these all things. Okay, so this was the vertical force, 638.09. You see, 638.09. This is vertical force. This is the horizontal force. So the vertical force is 638.09. Now the distance of CG of this vertical force from A, that will be moment about the load P, okay, P vertical. So this is the eccentricity of this load from A. Now we can calculate the eccentricity about the centroid. And the eccentricity about the centroid will be 2.5 into minus 2.16. So the eccentricity of this load is at this point from here. And this is what? 2.16. So the eccentricity about centroid will be to this value, 0.3. Now we know the moment and we also know the eccentricity. Know the load and know the eccentricity about centroid or middle portion. Now we can calculate the pressure by simply P divided by A plus minus M over Z. So M will be like PE, equal to PE. Okay. Hence bending moment about center, M equal to this one. This is the vertical load, this is the eccentricity, so the bending moment is this. Now the area of base is for 1 meter strip, the width is 5 meter, 5 into 1, 5 meter square. Modulus will be what? BD square by 6. So B is 1 meter, so 1 into 5 square over 6. Okay, this will become this. Direct pressure P over A, bending pressure M over Z. So the maximum pressure below footing will be this. The minimum pressure below footing will be this 180.36 and 74.87. We can also calculate the pressure at this point. This will be 146.61 and the pressure at this point by interpolation. At the face of this stem and heel slab and the face of stem slab and toe slab. Okay, because we will use these two pressure to calculate the bending moment at this location and these two pressures to calculate the bending moment at this location. Okay, these values we can easily calculate. Now the factor of safety against overturning moment was this about A, restoring moment was this. The factor of safety is restoring moment divided by overturning moment, it will come to 2.99, that is more than 1.50. And the factor of safety against sliding is, so active earth pressure was 4.55. The restoring force is sliding force, friction under the base. So vertical force was this, total vertical force, and the coefficient of friction is 0.65. So the restoring force is this one. Okay, this was PA, horizontal force we have calculated. Now we have calculated the total vertical force, downward force. I also know what is the coefficient of friction between the soil and the concrete. That mu is equal to 0.65. So the restoring force, this force will be equal to is 0.65 times W or P. W. We have neglected the contribution of passive earth pressure. Okay, if you consider the participation of this passive earth pressure, then this pressure we will have to add this PP. Okay, so the restoring force will become 0.65 times W plus PP. So we have neglected this participation of this passive earth pressure. Okay, so now the factor of safety will be equal to 414 divided by 214. It will become 1.93, that is more than 1.5. ठीक है, any question up to here? Am I audible?
Yes, sir, audible.
Okay. Okay, now we will calculate the moment and shear. So active earth pressure due to surcharge. So first we will calculate the moment and shear at this section, at this point. Okay, so the distribution is very simple here. Due to active earth pressure, triangular, and due to surcharge, rectangular. So due to surcharge is 5.42. So this is triangular, and due to surcharge it will be rectangular. And due to earth the pressure will be triangular. So earth pressure at the base of filling. So this value is what? 35.16, and this is constant value 5.42. So and what is height? Height up to here is 7.95 meter. So the force will be 5.42 into 7.95. 5.42 into 7.95. Okay, this is the force. Shear force. We are calculating now shear force at this location. And this triangular force will be equal to half into 35.16 into height. Okay, for 1 meter strip. So the now force will become at this location 182.87. So the shear force at this location will be 182.87. Again, the bending moment will be this force 43.09 into half of height, and again this force, triangular force, into 1/3 of height. So it will act here at 1/3, and this will act at half to calculate bending moment here. Okay. So the ultimate shear force will be 1.5 times this, and the ultimate bending moment will be 1.5 times this. This is load factor. Suppose this is 1.5. So the combination of is given in our code and also IRC 112. So we will apply that combination, and once we have obtained this ultimate shear force and ultimate bending moment, we can easily design our section. Okay. Suppose let the reinforcement are to be curtailed at height h1 from top. Suppose we are curtailing the reinforcement from height h1. So we will have to calculate the bending moment here. In similar fashion, we can also calculate the bending moment here. This is the triangular distribution. That will be the rectangular distribution due to surcharge, triangular due to earth filling. Okay. So the thickness at stem is this one that we have calculated because the thickness is 500 here and 1000 here. So we can calculate the thickness in between these two locations. So shear force, in similar fashion, we can calculate shear force. Okay, this is rectangular part, this is triangular part. The shear force is this. Again, bending moment at that location. Okay, and the ultimate shear force and ultimate bending moment we will obtain after applying load factor. Now to calculate the bending moment for hill slab, so we have calculated that the bending moment due to net soil pressure is at hill is 251.51 and 74.87. That we have calculated from here. From interpolation of these two extreme value, और ये हमने कैसे किया था, P over A plus minus M over Z. Okay, so this is 146. So this value is 180 and 146, and for stem it is for hill it is 125 and 74. So we are talking, I think, 180, 146. No, hill 125 and 74. Okay, so the distribution was like this. Okay, so these are the distribution of base pressure. Now we have also seen that at hill, this is the distribution of due to base pressure that will act upward, and there will be downward force due to soil above hill and due to surcharge, and that will act downward. The intensity will be constant. Okay, so this is 183.45, 183.45. So the net pressure distribution on hill will be like this, downward. So maximum at this point and minimum at this point. So this is 183 minus this, and 183.45 minus 74.87, we will get this. Now we will calculate from this force, and so now we will calculate our moment heel slab due to this downward force, 108.58 at this location, and this is 57.94. क्या करेंगे? We will divide this into two parts. Okay, so the bending moment will be the value of this force into lever arm will be at the center. The value of this force, lever arm will be like here, 2 by 3 into 2.40. Okay, so as say we can calculate the bending moment, that is for bending moment, the shear force will be the area of this distribution, triangular and rectangular. So the shear force will become 199.82, bending moment will become this 264.09. The ultimate shear force and bending moment we will get after applying factor of load factor. Okay. Again, into we have seen that into the force was this 180.36, 146.61. Okay, from soil that will act upward. Okay, now this is the suppose retaining wall. This is the soil pressure. It will act upward, and this is the pressure due to earth filling above this. That will act downward. The magnitude of this is 2020, and the net pressure will be 160 and 126. So 160 here and 126 here. So the final distribution for this toe slab is like this. Okay, so we will calculate shear force here by dividing this rectangular part, this pressure distribution into rectangular part and triangular part. Okay, so that force will be summation of this plus this, and the moment of this about this will be the force of rectangular part into this lever arm plus the force in triangular part into this lever. Okay, so With this, we can calculate the shear force to slab, that will be equal to 229.58, and the bending moment at the face of stem, that is equal to 190.86. So then by applying factor of safety or load factor, we can get the factored load. Okay. Now we have get the factored load for shear force and bending moment for the stem at this point, and at some point also for curtailment of reinforcement. We have also got the factored shear force and bending moment for maximum factored shear force and bending moment for toe slab and heel slab, for toe slab at this point and for heel slab at this point. Okay. So by these bending moment, we can calculate what will be the reinforcement by following the provision given in our CBC code or IS 456 or IRC 112. Okay, so we have calculated this, the reinforcement as per IRC 112. We have discussed several times how to design any slab or beam in shear, flexor. Okay, so we will not discuss this. Just go through the design of cantilever wall. So main reinforcement for the stem will be like this. Main reinforcement for heel like this, and the main reinforcement of this toe slab will be like this. And you can provide the distribution reinforcement accordingly as given in the different code, the value of different code for minimum reinforcement. Okay, we can also extend this up to this point and provide distribution reinforcement. So these are distribution reinforcement. So the main reinforcement will be from here to here. The requirement is these are the development length. Here the requirement for toe slab is from here to here. This is the development length. And for stem up to here, and this is the development length. Okay. We can also provide shear key if the factor of safety for sliding is less than 1.5 meter. By providing shear key, there will be passive earth pressure, and that will help to resist the sliding force. ठीक है? Any question up to here?
प्रोविजन है क्या कुछ मिनिमम रेनफोर्समेंट का?
मिनिमम रेनफोर्समेंट का स्लैब का प्रोविजन है ना, सारे जगह है दिए हुए 0.12%, 0.5%. See the main reinforcement तो आप निकाल लोगे, इसका स्टेम का ये reinforcement वर्टिकल, यहाँ ये हील स्लैब का और ये टो स्लैब का है. मेन reinforcement के बाद आपको डिस्ट्रीब्यूशन reinforcement सारे जगह देना पड़ेगा. For that you will have to follow the provision given in CBC code or IS 456. CBC और IS 456 में मुझे लगता है कोई जो provision है ना 0.12% and for HYSD bar and 0.15%, शायद वही है ना? So the provisions are given in different code. You will have to follow that. For temperature.
Main reinforcement के लिए सर.
Main के लिए. मेन के लिए तो बता दिया ना आपको पूरा shear force bending moment कैलकुलेट करके. अब डिजाइन देखो हमने बहुत बार डिस्कस किया, इसके लिए मैंने स्केप कर दिया उसको, पर मैंने रखा है इस प्रेजेंटेशन.
जैसे डिजाइन में भी कैलकुलेट किया तो अगर मिनिमम रेनफोर्समेंट चेक करना होता है तो इससे कम ना हो, उसके लिए
वो तो किसी सूरत में करना है ना आपको. जो मेन रीइंफोर्समेंट है, कभी भी आप मेन रीइंफोर्समेंट देते हो, बीम में कहीं भी आप मेन रीइंफोर्समेंट देते हो, कॉलम में, बीम में, कहीं भी आप देते हो, हर जगह प्रोविजन है मिनिमम. वो तो आपको चेक करना ही है भाई. ये बोल रहा हूँ कि 456 में जो मिनिमम रीइंफोर्समेंट है स्लैब का, दैट इज 0.12% और 0.15% इन केस ऑफ माइल्ड स्टील एंड HYSD बार. तो हाई स्ट्रेंथ बार्स के लिए 0.12% है, तो वो आपको देना है. मुझे लगता है कि प्रोबेबली सेम प्रोविजन शायद हमारे कोड में भी है, देखना पड़ेगा. बट दैट इज वेरी क्लियर, आप उसको पढ़ोगे तो समझ में आ जाएगा कितना देना. पर यस, आपको बेंडिंग रिक्वायरमेंट से अगर मिनिमम रीइंफोर्समेंट जो देना है टेम्परेचर सिंकेज के, उससे भी कम आ रहा है तो मिनिमम तो आपको देना ही है, उससे कम नहीं दे सकते. ठीक है,
थैंक यू सर.
एनी मोर क्वेश्चन?
बी वॉल का बारे में थोड़ा, बी वॉल दे सकते हैं सर रिटर्न?
नहीं, हाँ बहुत अच्छा क्वेश्चन है. देखो बी फोल दे सकते हैं, बिल्कुल मतलब सही क्वेश्चन है. बी फोल देखो बहुत जरूरी है, क्योंकि अगर आपने V4 नहीं दिया, सपोज करो ये सैचुरेटेड है पूरा फुल, तो आपका सैचुरेशन के कारण क्या होगा कि हाइड्रोस्टैटिक प्रेशर डेवलप होगा, ठीक है, दैट विल बी प्रेशर ड्यू टू वाटर, और तभी प्रेशर डिस्ट्रीब्यूशन जो है वो ड्यू टू सॉइल थोड़ा चेंज हो जाता है, थोड़ा कम हो जाता है ड्यू टू इफेक्टिव प्रेशर, तभी आप ना इफेक्टिव स्ट्रेस और इफेक्टिव प्रेशर सॉइल का लेते हो, है ना, बट द होल प्रेशर ड्यू टू अर्थ एंड ड्यू टू दिस पोर वाटर प्रेशर और प्रेशर ड्यू टू वाटर विल बी ह्यूज। तो आपको अगर रिटेनिंग वॉल को डिजाइन करना है, अगर आपने V4 नहीं दिया, देन यू विल हैव टू कंसीडर दिस पोर वाटर प्रेशर, ठीक है, और उसके लिए आपका रिटेनिंग वॉल बहुत हैवी हो जाएगा। तो डिसिपेट दिस पोर वाटर प्रेशर यू विल हैव टू प्रोवाइड V4, ताकि वो बैकफिल में ना पोर वाटर प्रेशर डेवलप ही नहीं हो, पानी आए V4 से निकल जाए। बट इफ यू आर नॉट प्रोवाइडिंग V4 for any region, then we will have to calculate the pore water pressure also. तो V4 तो आपको देना ही है, अगर नहीं दोगे तो थोड़ा हैवी हो जाएगा रिटेनिंग वॉल। और ये फेलियर्स भी हुए हैं, आपने V4 नहीं दिया और वाटर प्रेशर भी कैलकुलेट नहीं किया, तो रिटेनिंग वॉल आपका फेल भी हो सकता है, क्रैक्स वगैरह आ जाएंगे, इंक्लाइंड हो जाएगा वो।
सर जो इसमें जो बी बॉल का स्पेसिंग रखेंगे वो सर जैसे कि लाइक बिंग बॉल और रिटर्न बॉल के तरह ही रखेंगे सर?
हाँ बिल्कुल सही, जो प्रोविजन है वही रखोगे आप, और उसमें V4 भी देते हैं, और आप जो ग्रेनुअल फिलिंग की बात कर रहे हो ना, वो भी इसीलिए देते हैं कि V4 से वो पूरा आप ड्रेनेज सिस्टम भी क्रिएट करते हो उसके पीछे, कहीं भी चोकअप नहीं हो वो, है ना। इनफैक्ट बॉक्स के पीछे हम लोग V4 देते हैं क्या, बॉक्स डिजाइन में?
सर बॉक्स में बोल्डर का फिलिंग
करते हैं, V4 नहीं देते।
V4 तो
बॉक्स में V4 नहीं होता,
नहीं V4 नहीं देते बॉक्स में,
नहीं देते सर।
अच्छा ओके, अब V4 नहीं देते तो बॉक्स में फिर देखो आप, ऐसे बॉक्स है, मैंने समझा था उसको, डीजी बॉक्स है ना, और आपने रिटर्न वॉल बना दिया ऐसे, और
आवाज ब्रेक हो रहा है।
हाँ आपने वो बॉक्स बनाया, दिस इज बॉक्स, ओके, दीज आर स्ट्रेट रिटर्न। आवाज आ रही है
सर? वॉइस इज ब्रेकिंग।
ओके,
नहीं यहाँ आवाज ठीक है अविनाश तुम्हारा, देयर माइट बी सम प्रॉब्लम विद दैट।
तो
हाँ सर आवाज ठीक है सर।
ओके, तो ये बॉक्स में क्या है कि आप V4 नहीं देते हैं ना, ऐसे V4 नहीं दिया, अभी रिटेनिंग वॉल रिटर्न वॉल में अपने V4 दिया, पर यहाँ पे बोल्डर्स फिलिंग कर दिया आपने, करेक्ट, यहाँ बोल्डर्स फिलिंग करते हैं, है ना, एंड वी आर आल्सो प्रोवाइडिंग बोल्डर फिलिंग्स हियर, एंड वी जनरली we also provide the V4 in the straight return और wing wall, ठीक है। तो क्या होगा कि आपने एक चैनल बना दिया, you have created a channel, the water will go here, it will, ये चैनल से ये बाहर निकल जाएगा, तो पोर वाटर प्रेशर नहीं होगा, वो डिसिपेट कर देगा, although you are not providing here V4, okay, but you are ensuring that there is no creation of poor water pressure behind box। ये मेरे अंडरस्टैंडिंग से, हम लोग बॉक्स में नहीं देते हैं क्या शुक्ला सर, ठीक है?
हाँ ठीक है
ना, कि वो पोर वाटर आपने V4 तो नहीं दिया, लेकिन आपने बोल्डर फिलिंग किया है, ग्रेनुअल फिलिंग किया है, तो वो पानी को आप रिटर्न वॉल के थ्रू तो निकाल ही रहे हो इससे ऐसे, और अगर यहाँ जा भी रहा है तो वो ये चैनल से फिर निकल जा रहा है। Okay. Any more question?
What about construction joints? कितना लेंथ तक हम कंस्ट्रक्ट कर सकते हैं इसको?
Construction joint of retaining wall.
हाँ सर, कितना लेंथ मैक्सिमम हम कर सकते हैं?
तो एग्जैक्ट फिगर मुझे नहीं पता।
वो IS 456 में दिया हुआ है 40
मीटर है सर, 40
IS 456 में है।
कितना होगा अप्रोक्सीमेट?
हेलो,
हाँ अप्रोक्सीमेट कितना होगा वो
40 मीटर।
रिटर्न, अच्छा 40 मीटर।
रहा है कि इसका कंस्ट्रक्शन जॉइंट प्रोवाइड करने के लिए अलग से आईएस कोड भी है, उसमें भी मेंशन है, बट अप्रोक्सीमेटली 40 मीटर के आसपास है।
Yes.
Thank you, sir.
Okay, we will also look at some few very interesting and important provision of this CVC. और हमने उसका ये भी नहीं डिजाइन नहीं देखा था, तो we will look at provisions for shear, flexure and biaxial bending, है ना? So one very interesting provision is this one: the bridge shall be designed for the service life as given below. So we will have to design the bridge, whether that is RC bridge or pre-stressed bridge. So the bridge shall be designed for life of 50 years, 80 years and 100 years in sea, coastal area and rest of India respectively. ठीक है? पर ये कैसे इंश्योर करेंगे? How we will design for 50, 80 and कोई जवाब? Opinion?
Sir, on the environmental conditions and this.
सर सर्विसेबिलिटी क्लास को फॉलो करके
नहीं, वो ठीक है, लेकिन उससे 50 इयर्स हो जाएगा। मतलब देखो, द ब्रिज शैल बी डिजाइन फॉर द सर्विस लाइफ एज गिवन बिलो। तो यू आर डिजाइनिंग द ब्रिज फॉर 50 ईयर सर्विस लाइफ। जैसे यू आर डिजाइनिंग योर बीम फॉर बेंडिंग मोमेंट ऑफ 100 किलोमीटर पर मीटर in for ultimate load and suppose 75 kilometer per meter for service condition. Okay, so that is clearly defined, and there are rational way to calculate the ultimate load carrying capacity, and that should be more than this 100 kilonewton meter. And we will also calculate the stresses for this load, service load, and the stresses should be, and the crack width should be within the limit. So there are rational methods to calculate this capacity and the stresses and the crack width of maximum crack width. Okay,
सर फैटिग क्राइटेरिया
मेथड टू कैलकुलेट है,
फैटिग क्राइटेरिया से भी कर सकते हैं।
इससे
फैटिग
नहीं फटीग इसमें कहाँ? ओके
सर एक डाउट,
ठीक है, स्टील ब्रिजेज में फटीग से हम लोग एक उसका कैलकुलेशन करते हैं, लाइफ ऑफ दैट स्ट्रक्चर। ओके, दैट इज एप्लीकेबल फॉर स्टील ब्रिजेज। कंक्रीट में किया है क्या किसी ने? ठीक, इन कंक्रीट कोड ना, इन आवर कोड आल्सो ओनली वन प्रोविजन इज गिवन रिगार्डिंग फटीग, that is you will have to restrict the stresses in the reinforcement. That is given in one clause. That is the fatigue criteria. The only thing you will have to ensure that the stresses in the steel are within that value. शुक्ला सर, इसका कुछ तो नहीं है ना?
वही वो सर्विसबिलिटी लिमिट स्टेट है बेसिकली, और बाकी जो लाइफ के लिए जो है वो क्रैक विड्थ, एक्सपोजर कंडीशन एंड क्रैक विड्थ।
सर मैं ये जानना चाह रहा हूँ कि द ब्रिज शैल बी डिजाइन फॉर सर्विस लाइफ एज गिवन बिलो। वेदर हम लोग डिजाइन कर रहे हैं क्या ब्रिजेज को 50?
नहीं, इसमें इसके लिए जो आप एक्सपोजर कंडीशन लेते हैं ना,
एक्सपोजर
मैं क्लियर कर देता हूँ। देखिए, जो एक्सपोजर कंडीशन है, जो भी लिखा हुआ वो प्रोविजंस भी हम लोग थोड़ा देख लेंगे। That is for to achieve a durable structure, but उसको कनेक्ट किया है कि वो हमने अगर फॉलो कर लिया तो हम ये मान लें कि हमारा ब्रिजेज इज फॉर 50 years, that the bridge will survive for 50 years in sea or 80 years in coastal area or 100 years in rest of India.
इसमें
उसके बाद क्रैक विड्थ आप लिमिट करते हैं ना, वो डिफरेंट एक्सपोजर कंडीशन के लिए अलग अलग है।
That you can calculate the डिजाइन लाइफ ऑफ ए स्ट्रक्चर। अगर आप उसको 300 साल के लिए करना चाहते हो, जैसे बर्ली बांद्रा सीलिंग है, उसको कुछ 250 साल के लिए किया है सर, मतलब मुझे करेक्टली याद नहीं कर रहा हूँ, पर उसको कुछ एक लाइफ के लिए डिजाइन किया है। तो दे मस्ट हैव डन सम टाइप ऑफ रेशनल कैलकुलेशन और सम टाइप ऑफ मॉडलिंग और कैलकुलेशन को किया होगा उन्होंने, है ना?
इसमें अविनाश,
तरीका ये है कि यू कैन डिजाइन एनी ब्रिज बाय फॉलोइंग सम प्रोविजन and you can calculate the service life of that bridge. जैसे कि अभी आपने rightly वो mention किया कि in case of steel girder we are performing the fatigue analysis to know the rest life or the total life of the girder, steel girder as per fatigue provision. ठीक है, तो वहां आप एक रेशनल तरीके से देख रहे हो कि कितने साइकिल में वो फेल करेगा, हर एक साल कितना साइकिल ऑफ नंबर ऑफ साइकिल्स लोड लग रहे हैं. इन दैट वे यू आर कैलकुलेटिंग द लाइफ ऑफ द स्टील गर्डर. लेकिन यहाँ पे कंक्रीट ब्रिज कोड में सिर्फ ये लाइन, इस लाइन का मतलब मेरे हिसाब से ये लाइन मेंशन किया हुआ है. तो अभी तो हम यही मान के चलते हैं कि इफ यू वी आर फॉलोइंग द प्रोविजन गिवन फॉर ड्यूरेबिलिटी एज पर ड्यूरेबिलिटी क्राइटेरिया given to ensure a durable concrete, then we can assume that our life of the structure will be what is mentioning in our code. Okay, similar to what is mentioned in our code.
May I interview? अविनाश,
पर मुझे लगता है कि बाकी जगह जो है वो मॉडल वगैरह बना के, बहुत सारे मॉडल हैं और आजकल लोग कर रहे हैं, तो कंक्रीट ब्रिजेस की भी लाइफ को प्रेडिक्ट करने का बहुत सारा तरीका है.
अविनाश,
but that is not mentioned in our code. Okay.
सर के पास आवाज नहीं है.
अविनाश,
to achieve a durable concrete, a proper drainage system shall be provided.
ठीक है, ऐसे कोई बोलता है तो कॉलिंग, मुझे लगता है कि आवाज नहीं आ रही है क्या? मैं कॉल करता हूँ. हाँ, आवाज. हेलो अविनाश,
am I audible?
हाँ, तुम्हारी आवाज आ रही है. अविनाश, लगता है अपनी आवाज नहीं जा रही उसको.
Yes sir.
Okay, am I audible?
Yes, you are audible. Are you getting?
Yes sir. Yes sir. Automatic sir.
Okay. I wanted just to add one thing here. कि ये जो हमारे प्रोविजंस है, व्हाट यू आर डिस्कसिंग, एंड वेरी राइटली आवर assumption is that if we follow the provisions regarding durability in our concrete bridge code, then we are likely to get that life of the bridge. इसमें एक बहुत इंपॉर्टेंट प्रोविजन है जो ड्यूरेबिलिटी को लेके है, वो है आपका परमिबिलिटी टेस्ट और परमिबिलिटी की लिमिट. इसमें I am not seen in our codes that people are mentioning that our drawings people are mentioning that you have to perform this test and what should be the limit of the water penetration in that. So my advice is that in the drawings we should start mentioning that. Otherwise field में बहुत लोगों को पता नहीं है and by and large that test is not done. So I think we should start mentioning that test in our notes. जो drawing में हम notes लिखते हैं उसमें उसको specifically mention करना जरूरी है, so that attention of the field engineers is invited to that. Yeah, Avinash, you can continue.
Okay, yes. Okay, so as per clause 15.2.2, a proper drainage system shall be provided on the deck as indicated in 15.2.2 provided to ensure durability. For other durability requirement of concrete like maximum water cement ratio, minimum grade of concrete, minimum cement content, maximum crack width, etc., clause 5.4 and 10.2.1 shall be referred. Okay, so there are few clauses to ensure to achieve a durable concrete. So we should ensure the proper drainage of the deck. Okay, the first is that. The second is we will have to provide a minimum cover depending upon the environmental condition. So in slab that is 50 mm, in extreme environmental condition is moderate 25. So there are three environmental conditions mentioned in our code. So in IS code I think there are 5 environmental conditions, but we have mentioned only we have included only 3 environmental conditions: extreme environment, severe environmental condition, moderate environmental. Okay, so these are the minimum value of clear cover to be provided to achieve a durable concrete. This will also restrict the crack width depending on the environmental condition. So in case of moderate environmental condition, the maximum crack width should not be more than 0.25 mm. For severe, it should be not more than 0.2 mm, and for extreme condition it should not be more than 0.1 mm. So as we increase the severity of the exposure condition, we are restricting the maximum width of the crack. Okay, so we have also restricted the maximum water cement ratio that is given in clause 543 and table 4a. Okay, so you can refer this one also. Now the minimum grade of concrete is also given So in case of pre-stressed concrete or important bridge construction. So in case of reinforced concrete, if the bridge is important, then we will have to ensure this condition for PCC, RCC and PSC, the minimum grade of concrete for moderate, severe and exposure condition is given here. But in case of other bridges of reinforced concrete, we will have to follow the table given in B. So in case of RCC and PSC, depending on three exposure condition. Okay.
There is some problem with the connectivity, internet connectivity of Avinash. He is getting locked out frequently. So he is trying to connect again. So please wait for a few minutes.
So as we are running short of time, so I will go a little fast, okay? So the minimum cement content is given in table 4C, okay? But at the same time, content is also restricted in our code, and that is 500 kg per meter cube. So in no case we can use concrete more than 500 kg per meter cube. This value is restricted also in IS 456, but there the value is restricted as 450 kg per meter. So we are permitting actually higher value, and the reason for restriction of this value is if we apply more cement, there are chances that the cracks will be more due to shrinkage and temperature. Okay. So due to serviceability, we have also restricted the stresses in service condition. So for triangular or near triangular compressive stress, so in case of bending, the maximum stress in concrete should not go more than 0.5 FCK. In case of direct compression, the maximum stress should not go more than 0.3 FCK, and in steel in service condition, the maximum stress per meter is 0.75 FY. Okay. So in steel, we don't want yielding of steel in service condition to restrict the inelastic deformation in our structure, and to restrict also the crack width. If the strain in the reinforcement will be more, there are chances that the width of crack will be more. Okay. So that's why we are restricting the stress in steel in service condition 0.75 FY. The restriction of stress in concrete equal to 0.5 FCK in bending or 0.38 FCK in compression is because first is due to there will be macro cracks. The macro cracks may appear in the concrete if the stress in concrete will go higher than 0.6 to 0.7 times FCK. Okay, the first reason is this. The second is due to creep, because the creep is proportional to stress up to 0.5 FCK. Okay, so at the higher stress, if the stress in concrete in service condition is higher, there will be chances that the creep strain will be more. Okay, so to restrict or minimize the creep strain and to restrict the initiation of micro cracks, we generally restrict the stresses in service condition in concrete. Okay. Now these are a few clauses of CBC, which is for bending. These are similar to our provisions given in IS code. So the first provision in plane section remains plane after bending. The second is the stress in the concrete in compression are either derived from the stress strain curve that is given in 4A, okay, with Ym equal to 1.5, that is similar to our IS code, and also as per IRC. In case of rectangular section, in flange, reeved and voided section where natural axis lie within the flange, the compressive strength may be taken as 0.4 FCK over the whole compression zone. Okay. In both the cases, the strain at the outermost compression fiber is taken at 0.0035. So we calculate the compression in concrete either from this curve, or we can calculate the compression in concrete by taking the compression equal to average compression equal to 0.4 FCK. Okay. The tensile strength of concrete is ignored. The stress in the reinforcement are, these are provision given in CBC code. Okay, the stresses in the reinforcement are derived from the stress strain curve for steel, and the partial safety factor for steel is taken as 1.15. The partial safety factor for concrete is taken as 1.5. That is similar to the provision given in IS 456. And the maximum strain in the reinforcement should not be less than this. So this provision is given in IS 456. So the provision of CBC for flexure is mostly similar to provision of IS 456. Okay. This provision was not there in IRC 112. Okay. Now, so the average stress we can assume at 0.4 FCK, and the depth of neutral axis has been assumed 0.5 D, which is not very rational, but it is assumed in our code. And from there we can calculate this force, compressive force. This compressive force will be equal to, this bending moment is equal to, so see, this is 0.4 FCK, this is 0.5 D. The centroid will be here. If we calculate this lever arm, this will become 0.75 D. Okay. So if you multiply this compressive force is 0.4 FCK to 0.5 D, this is compression into this lever arm, 0.75 D. So we will get this value, 0.15 FCK BD square. So this value is very on conservative side. That is not accurate, but that is what is given in our CBC code. So we are not calculating the depth of neutral axis. We are assuming the depth of neutral axis equal to 0.5 D or the average stress equal to 0.4 FCK. Okay. So the bending moment will be equal to this also, 0.87 Fy, the stress in steel, concrete, and Z is the lever arm. The value of Z is also given in our code. Okay. For section without compression reinforcement, the ultimate moment of resistance may be taken as the lesser of the value obtained from the equation 1 and 2, and equation 3 and 4 may be used for section with compression reinforcement. Now look at equation 3 and 4. So Mu is the compressive force. This is due to compression block, and this is due to this reinforcement. Okay. ASC or AS. So the stress has been taken equal to 0.7 Fy. Okay. Whereas as per IS 456, you will have to calculate this strain depending on the strain compatibility and the location of this bar from here. So the distribution will be like this, 0.0035. You will have to calculate the strain here, and from strain we were calculating there the forces in compression steel, but here it is given directly 0.72 Fy as D minus D dash. Okay. And these are the force equilibrium. Tension in steel, this is, you see, 0.2 FCK BD, because 0.4 FCK into 0.5 D will be equal to 0.2 FCK BD plus this force in steel. So the tension in steel equal to, tension in steel will be equal to compression in concrete plus compression in steel. Okay. From this equilibrium, we will get the neutral axis. But here you see there is no provision to calculate the neutral axis. You know everything. What is AS, what is Fy, what is B, what is D, what is FCK, what is Fy, what is AS. So if it doesn't follow the equilibrium, I don't know what to do, because no variable is there in equation 4. So this equilibrium equation we generally apply to calculate the neutral axis. Okay. So the equation 1 to 4 is given in our CBC code. Okay. For shear stress, we will calculate the shear stress by dividing the shear force. For BD, the maximum compression in compression stirred, or in no case this shear stress will be more than this value, 0.75 times root under FCK, or 4.75 Newton per mm square. Okay, just to avoid the compression shear failure or the compression failure of strut. Okay, compression failure of concrete. So B is the shear force due to ultimate load, B is the width, and D is the effective depth. Okay, here also for that the formula is given. This is for minimum shear reinforcement. This is for the shear stress with shear reinforcement. Here S is B is the shear force. Here interesting thing is S is the depth factor. Okay, as we know, as we increase the depth of the beam, the shear resistance due to concrete alone will reduce. Okay, so that factor has been included in our code. So you see here what is S. So if the effective depth is more, S will be less. Okay, and the effective depth is less, S will be more. So we can take maximum value of S if the thickness of slab or beam is less than, or the slab is less than 100 mm, that is 1.50, and we reduce this value up to 0.7 if the thickness of the slab or beam is more than 2000 mm or 2 meter. Okay. So the equation is also given S equal to 500 divided by D power 14 or 0.7, whichever is greater. These are the value of TOSI, the strength of concrete. Okay, it will depend on the area of reinforcement over BD. So the percentage of reinforcement, the grade of concrete, and the maximum value is restricted up to M640. That is similar to IS 456. Okay. In IRC 114, this grade is restricted to M6. Now, we have seen the increase in strength, shear strength. See, first is the increase of shear strength due to depth factor. If we increase the depth, the shear strength of concrete will reduce, or if we decrease the depth, the shear strength of concrete alone will increase. Okay, but we have also seen that if the load, this is support, and the load is within 2D. Okay, this is 2D, and suppose this is AB. If this AB is less than 2D, then the strength of concrete, since the load will directly go to the support, so the shear strength of this at this location will be higher from this location. Okay, so we will have to take this action also into account. So there were provision in IRC and also in IS code that we will divide this force, we will reduce this force P by AV over 2D. Okay, and we will have to design, we will design this shear at this location with this reduced value of load. Okay, but in our code, we are increasing the shear strength at this location. Okay, so enhance shear strength of section close to support and enhancement of shear strength may be allowed for section within a distance AB less than 2D from the face of the support, from edge of the rigid bearing or center line of a flexible bearing. The enhancement shall take the form of an increase in the allowable shear stress SBC or mu C to S mu C into 2D over AB, but shall not increase this to avoid the crushing of concrete. Okay, whichever is lesser. Where this enhancement is used, the main reinforcement at the section considered shall continue to the support and be provided with an anchorage equivalent to 20 times the bar diameter. So we have also discussed that in case of strut and tie, we will have to anchor the reinforcement beyond the support to a considerable distance so that the required tension can develop. ठीक है, वो snapping of bar नहीं हो जाए वहां पे. ठीक है. So in case of IS 456, we have seen that in case of IS 456 and IRC 114, we were reducing the force load, but here we are enhancing the shear strength. तो उसमें problem क्या हो रहा था? If we are reducing the load, suppose we have 2 or 3 combination of load here. One is this, one is this. So we will reduce this P1 and P2 according to the distance AB1 and AB2. Okay. AB1 and AB2. So we will reduce this force P1 equal to P1 into AB1 over 2D and P2 equal to P2 into AB2 over 2D. Okay. So we will reduce the load and we will design the whole section with this reduced load. But in case of this provision, this is applicable only in case of one load because you are increasing the strength here. So in case of two load, what to do, that we will have. Now this is analysis for column. This is also similar to our IS code, but the value 0.4 FCK has been taken also here, the average value of stress. Okay. Now for biaxial bending, we will do the same thing. Mx over Mux, My over Mui, alpha n. Mx is the applied, Mx and My is the applied load. Mux and Mui is the load carrying capacity due to this axial force Pu. Okay. Then we will calculate this alpha n with the ratio P over Puz. P is the applied load. Puz we will calculate from this formula. Okay. Then once we get alpha and this value Mux and Muy, we will apply this interaction equation to see whether our section is capable to take these loads or not.